Castor, or its scientific name, Ricinus communis, is a member of the Euphorbiaceae family. It is an oilseed plant cultivated in tropical and semi-arid areas like Iran. It is native to East Africa, the southeastern Mediterranean basin, and India. It is now widespread in tropical areas and often used ornamentally. The plant is a short, dry photoperiod crop, of which the emergency period to mature lasts within 100 to 150 days, which is about 3 to 5 months. Castor is the key source of non-edible vegetable oil in arid regions. The size and color of its seed vary within the species, so the understanding to the thermal threshold for different castor types is crucial due to its economic and agricultural significance. The temperature and moisture greatly influence the germination and seedling development, since it is essential for the stages in the plant's life cycle. The relationship between seed size and seed germination heat threshold is not well understood and is not well studied, although there are some studies suggest that seed mass will affect the germination percentage. Darker seeds show lower electrical conductivity and higher germination potential as compared to the lighter seeds. In oilseed rape, larger seeds have high germinability, and darker seeds they maintain quality longer in storage. Seeds need uh, seeds need suitable thermal, moisture, and light conditions for optimal germination and seedling survival. It is unclear to what extent that the seed size and seed color will influence the thermal thresholds of seed germination. Quantifying the cardinal temperatures of seed germination in plant species can actually help farmers to identify the optimal sowing period at their geographic location and to predict the field establishment under different thermal scenarios.
For the investigation, it has divided into three parts. The first part is the research methods. This study investigated castor bean seed germination using two genotypes, greens and red leaf varieties. Seeds were divided into small, which is 2 until 2.5 mg, and large, 3 until 3.5 mg size classes. Germination tests were conducted under controlled conditions in germinators. Seeds were tested at constant temperature from 5 degrees Celsius to 40 degrees Celsius with 5 degrees Celsius intervals. The aim was to examine how temperature, seed size, and genotype affect germination. The second part is the data collection. For each treatment combination, three replicates of 25 seeds were used. Seeds were placed in petri dish between filter papers moistened with distilled water. Germination was monitored every 6 hours for the first 4 days, then every 12 hours until day 14. A seed was considered germinated when its radicle protruded at least 2 mm from the seed coat. Germinated seeds were counted, removed, and expressed as a percentage of total seeds tested. This process was repeated for each combination of seed size, genotype, and temperature. The last part is the data analysis. The data analysis involved plotting cumulative germination percentage against time for each treatment. A logistic model was used to determine seed germination fraction with the formula G equal to G max divided by 1 plus e to the power of s times t minus b. Here, here G is the germination percentage, G max is the maximum germination percentage, S is the slope of the line, T is the time in hours, and B is a constant. Germination rates were calculated using the formula GR equals F in bracket of H divided by FO. In this equation, F in bracket of H is the temperature reduction factor ranging from 0 at base and ceiling temperature to 1 at optimal temperature. And FO represents the minimum hours required for seed germination at the optimum temperature. Various nonlinear models, which is beta, beta modified, segmented, and then-like, were calibrated using Sigma plot software. Daily thermal time was calculated as dTT equals TO minus TB multiplied by FH. Here, TO is the lower optimum temperature, TB is the best temperature, and FH is the temperature function. Finally, root mean square error and coefficient of determination were used to determine the best parameters estimate. This method allowed for a thorough examination of the effects of temperature, seed size, and genotype on castor bean seed germination. Thank you.
For the findings, we are talking about the seed characteristics are affected by the other factors. From the beta modified models and the study, we can know what is the seed characteristic and the factors that affect the seeds. Seed characteristics are investigated. The association between seeds, size, color, and germination rates are investigated in this study using nonlinear regression models. The factor affects seeds. The degree to which these seeds characteristics affect cardinal temperature and the thermal time requirements for seed germination was evaluated. Study, we are using beta modified models, which is the most accurate in forecasting the amount of time needed to achieve 50% germination. In this study, the cardinal temperature, seed germination rates, and seed traits and modeling germinations are the findings to identify the seed size, color affected by the showing many results. Study, we are using beta modified models, which is the most accurate in forecasting the amount of time needed to achieve 50% germination. In this study, the cardinal temperature, seed germination rates, and seed traits and modeling germinations are the findings to identify the seed size, color affected by the showing many results. 4.49 to 8.59 degrees Celsius, which is the best temperature, 19.76 to 21.88 degrees Celsius, which is the ultimate temperature, and 34.12 to 41.68 degrees Celsius, which is the maximum temperature, are identified, which means larger seeds have larger base, and ceiling temperature compared to the smaller seeds. Based on figure 2, seed germination fractions of 10%, 50%, and 90% in larger reddish-brown seeds are required thermal time based on pool data when T2 equal to optimum temperature. So we are talking about the first part, germination rate and seed traits. The thermal times required for 50% germination vary significantly with the size and color. Small greenish gray seeds, 18,090 degrees per hour. Largest greenish gray seeds, which means 954 degrees per hour. Small reddish brown seeds, which is 15,051 degrees Celsius per hour. Large reddish brown seeds is 1,188 degrees Celsius per hour. Greenish gray seeds generally had a lower germination rates compared to the reddish brown seeds, potentially due to the lower seed vigor and viability. Based on figure 2, seed germination fractions of 10%, 50%, and 90% in larger reddish brown seeds are required thermal time based on pool data when T2 equal to optimum temperature. So we are talking about the first part, germination rate and seed traits. The thermal times required for 50% germination vary significantly with the size and color. Small greenish gray seeds, 18,090 degrees per hour. Largest greenish gray seeds, which means 954 degrees per hour. Small reddish brown seeds, which is 15,051 degrees Celsius per hour. Large reddish brown seeds is 1,188 degrees Celsius per hour. Greenish gray seeds generally had a lower germination rates compared to the reddish brown seeds, potentially due to the lower seed vigor and viability.
Seed selection is a key for better castor bean production. We need to focus more on seed size and color. First, larger seeds are better for germinate faster at ideal temperature and need less time and heat to sprout. Second, seed color matters. Reddish brown seeds outperform greenish gray ones. It is also higher germination rates and also sprout with less time and heat. Best seeds for planting is a large and reddish brown with combined high germination rates with quick sprouting. These results match other studies from Drummond et al. 2019. Heavier seeds tend to germinate better. Seed quality depends on where the seed grows on the plant. When the seed develops, earlier formed seeds usually have better quality. For recommendation, create a grading system based on size and color. This could boost germination rates and make cultivation more efficient. Temperature control is crucial for castor bean seed germination. The ideal temperature for castor bean germination is between 19.76 degrees Celsius and 21.88 degrees Celsius. Higher temperature within the ideal range speed up germination but can also cause heat stress if too high. We have three factors influencing temperature sensitivity. First is seed size. Larger seeds are more sensitive to temperature. Second, seed treatment. Different treatments may affect temperature tolerance. And third, seed age. Younger seeds are more sensitive to temperature. Temperature recommendation for management. We need to keep environment within the ideal range, which is 19.76 degrees Celsius to 21.88 degrees Celsius, and avoid prolonged exposure to temperature above 35 degrees Celsius. Harvesting practices significantly affect seed quality and germination potential. For seed maturation patterns, not all seeds mature at the same time, and later harvested seeds often have poorer development, which is smaller size, lower density, and weaker vigor. There is importance of phase harvesting, which is collect seeds at optimal maturity intervals and prioritize early matured seeds for superior quality. They have several factors influenced by harvest timing. Firstly, seed coat characteristics, which directly affects germination success. Secondly, seed density. While early harvested seeds tend to be denser, and denser seeds perform better in germination. Seed age at harvest. Younger seed shows greater adaptability to temperature fluctuations during germination, while older seeds are less resilient to temperature changes. There have several benefits of a well-structured phase harvesting strategy. First, elevates overall seed quality. Second, improves germination rates. Third, promotes uniform crop establishment. And last, potentially increases yields in subsequent planting. We have recommendation for harvesting practices, which is implement a phase harvesting approach and focus on collecting early matured denser seed. And lastly, combined with proper post-harvest management and storage techniques. I have two effective seed treatments for castor beans. First, scarification, which is scratching the seed coat, and secondly, swarm removal. The purpose of these treatments is to break seed dormancy, because dormancy is a natural delay in germination. The benefits of these treatments is for faster sprouting and more consistent germination. There is three important considerations. Firstly, temperature adjustment. Treated seeds may require different germination temperature, which is need to optimize condition for treated seeds. Secondly, seed age. It can influence treatment effectiveness, which is older seeds may respond differently to treatments. And thirdly, storage history. How seeds were stored affects treatment outcomes, which is proper storage is crucial for maintaining seed viability. The overall impact: significant improvement in germination rates, enhanced uniformity in castor bean crops. So the strategy for implementation for seed treatments is the treatments should not be used in isolation and need to consider alongside other factors, which is temperature control, seed quality, and storage conditions.
Okay, the research from Iran sheds light on how seeds and color influence germination success in castor bean, specifically Ricinus communis. And this study actually revealed that larger seeds generally germinate faster and more efficiently than smaller ones. Surprisingly, reddish brown seeds exhibited superior germination characteristics compared to greenish gray seeds. And the difference might be attributed to the higher viability and vigor of reddish brown seeds. And this research actually highlights the importance of selecting seeds based on size and color for improved germination rates and crop establishment, specifically crucial in semi-arid regions where water availability can be a limiting factor. And this research not only enhanced our understanding of the castor bean germination in terms of the ecology, but it is also provide practical guidance for farmers. So by implementing this information, the farmers can potentially optimize germination success and ultimately boost their castor bean yields.